Welcome everybody to today's webinar. My name is Dan Combest, and I'll be talking about scalable and accurate automotive simulation with elements. In terms of webinar goals, if you've attended one of these webinars before, you know that I always want to introduce ENGYS's CAE innovations, what we're doing, what makes us different. So I'll try to hit on that. I'll discuss where elements fits into the engineer's toolbox for automotive OEMs. Think of the big picture. And then I'm hoping to engage in conversation about how to solve tough automotive problems after the webinar, beyond the webinar. So hopefully this is just the beginning of good questions. And then as always, we'll answer questions at the end of the webinar. And if you have something that you want to continue afterwards, you can reply to the email directly from GoToWebinar, and that will go to me, and I will return an answer. Today's agenda, I'll talk about Aero-Thermal Complexities, I'll talk about elements, I'll talk about wind tunnel validation, I'll talk about a few success stories, elements GUI, and then some take-home messages. So let me start with Aero-Thermal Complexities. As aerothermal CFD engineers, there's a variety of different problems that we can work on. So if you're an aerothermal engineer, you may look at this and say, water management, why is this on there? Where there are aero interactions within water management, there's aerothermal interactions within human comfort, within cooling system performance, brake cooling, soiling, aero performance, aero design. So it's not just external aero. We have to think about different systems working together. And we do this to get the most bit of information out of our simulation data. Of course, we can work on each one of these in a discrete manner. We can talk about HVAC optimization with adjoint. We can talk about brake cooling. But if we think of the bigger picture and how these different systems interact with each other, it's going to provide a tremendous amount of intelligence about the overall performance of a vehicle in different scenarios and really help with decision making. As managers, there's a lot of team complexities that we have to deal with. The big picture is that whatever design changes or whatever design information that we find or any changes, it has to maintain design aesthetic. There's certain look and feel of a vehicle that no matter how much we want to change, OEMs have to keep a certain look and feel. It's also a necessity that we deliver accurate results. And delivering accurate results on time, under budget, it's a difficult task. Next, as a team, we have to think of the big picture and we have to optimize energy budget. So I'm speaking in terms of an energy budget, in terms of we're trying to maximize range of an EV. So there's lots of these different subsystems that have to work together that we have to think about. And how do we optimize our cooling system because it does interact with the external air flowing over the vehicle? We also have to think about working with global teams. So teams are located in different regions. You may be in the same city and everyone's sitting at home, but we have to think about how these teams work together effectively. There's teams with diverse levels of experience. How do you bring on someone who's very new to the process? How do you bring them into the fold and maximize their value to the team, maximize their experience, and really lower kind of the time to value? Kind of bring them on the team very quickly. And then finally, we need to optimize HPC resources and budget. So automotive, external aero for automotive, that simulation, those take many, many cores, and we need to do many, many runs. So really, the paradigm that we're working in, parallel licensing, isn't really going to work. So in terms of aerothermal solutions, we need to accelerate aerothermal design cycles and really deliver on time. And that may be a no-brainer, but Elements is an automotive specific simulation framework that is designed, the goal is to actually achieve this. We want to reduce software license expense to work with limited HPC resources and budget. You may say, oh, I have unlimited HPC resources, but there is a limit. It would be nice to save money on HPC. It would be nice to save money on parallel licensing. So within Elements, there is no parallel licensing restrictions. So we're completely not just reducing bottlenecks, but we're completely eliminating that HPC limitation, and you can spend that money in other ways. More HPC resources, more personnel. We also want to reduce the risk of using simulation results in decision making. So these are wind tunnel validated approaches. The methodology that's used within Elements, there are numerous cases of both ENGYS and our customers getting very good results. Very good results compared to experiment, very good results compared to other much, much more expensive software. And then finally, talking about reducing time to value, bringing on people onto a team very quickly, we want to reduce the human error within your team's simulation activities. So this is done very well and handled very well through the Aero-Wizard that we use to set up identical cases and automate the CFD process within Elements. So these are some of the things that I'll be talking about today. Let me start with Elements itself. Elements was a collaboration between the Auto Research Center out of Indianapolis, who are experts in automotive engineering, research and development. They have experimental setups. They have their own wind tunnel. And they're also experts in CFD application in the automotive arena. Then we have ENGYS. We're CAE software engineering experts. We have experience in CFD, MDO, multidisciplinary design optimization, development support. We've supported teams around the world with various levels of experience, from extremely knowledgeable users to people that have never used CFD before. So our two companies came together in a joint venture, and we've created Elements. There are several different components of Elements. The first and foremost is the Aero-Wizard. It's an aerodynamic setup wizard that automates a lot of the meshing best practices: what size of cell, how many layers, how do we mesh different components, the boundary conditions, what kind of boundary condition does a body panel receive versus what kind of boundary condition does a wheel receive. So a lot of this is automated within the Aero-Wizard. Next, we have the general CFD GUI. So this is a general purpose CFD analysis tool. So it goes beyond just external aero to do things like conjugate heat transfer. There's some multi-phase capability. There's other types of CFD that we may be doing within our automotive simulation teams. The actual core behind it, so the solvers, the mesher, the utility, is all open source. So this is how we're able to deliver a solution that doesn't have parallel licensing limitations. There's also a component of Elements add-ons. So we're able to offer solver extensions, additional features, for example, continuous adjoint optimization. This type of technology is used for optimizing internal flows, for topology optimization, so change the actual shape of, say, a duct, an air conditioning duct. Or we're able to obtain information about the external flow and give information about sensitivities on the surface. Where should we push in or pull out on a surface to reduce drag or reduce lift or increase lift, or whatever we need to do to control the flow. So it augments our decision-making capability. Every license of Elements comes with user support. There's code maintenance. There's numerous releases during the year with new features and bug fixes. And then there's extensive documentation with information about the core, with information about the mesher, the solvers, and then also tutorials to help people that are new to the software to learn how to use elements very effectively. Now, using the external aero interface, there's 4 main steps. The first being setting up a case for the external aero itself. Then there's creating a mesh, running a case, and then running and evaluating this report that's output. In terms of a report, it gives aero case information, lift and drag data, extensive volumetric data images, so slices, isosurfaces, streamlines, surface plots. This report is customizable, and we can obtain further data through in situ runtime post-processing. That means that we're able to output images during the solving step without actually outputting a lot of data. And if we know what we're looking for ahead of time, this is extremely powerful. And if you want animations, this is a great way to do this. I actually have an entirely different webinar on this topic itself. Now, we can go further. Because we're outputting all of this data, that means that there's potential to take this lift drag data or other probe data and do further data analysis. So there's not just images, it's data on all different levels that we're able to extract from simulations themselves. Okay, so that's just a brief introduction to elements. Let me talk about the wind tunnel validation efforts. This is a cornerstone of elements itself. One of the strengths is that it was built on the idea that this software is validated against wind tunnel data. And this data was collected by our partner, and a lot of the experiments were performed by the Auto Research Center. So the main objective of this wind tunnel validation effort is to actually validate the best practices for the external aerodynamics CFD. So all of these templates. The requirements of this were extensive wind tunnel measurements by ARC and other OEM wind tunnels. And we wanted to be able to capture a lot of, a wide range of vehicle shapes. We didn't want to work with just motorsport. We wanted to be able to work with motorsport and sedans and squarebacks and different vehicle shapes and commercial trucking. So there's lots of different shapes that have been, results have been collected. The outcome of this process is input into our automatic CFD process in order to give consistent drag prediction across multiple vehicle shapes to improve its accuracy within a specified level of error. And there's a nice reference from 2014 if you're curious about the methodology. Very nicely written white paper by my colleagues, some of whom are on this call. Some of the vehicle types that were captured during this wind tunnel validation effort: sedans, hatchback, estate backs, SUV, streamliner, NASCAR, IndyCar, light and heavy duty trucks. There were over 200 different test configurations on all these different vehicle types. So these different test configurations could be different configurations of the wind tunnel, or we're talking about different speeds, different yaw angles, different ride heights, different vehicle modifications. So open or closed cooling, spoilers on or off, underbody panels on or off, air dams on or off. So there's lots of different configurations for these different vehicle types in order to give us a better understanding of this structure-function relationship, to know exactly how we should mesh and how we should apply a best practice in order to capture not only the right deltas or the right differences between these changes, but also the right direction. Does that reduce the drag or increase the drag? In terms of cars, so we've got a variety of different vehicles here. To summarize, the average error in magnitude for drag was around 1.2%. For front lift and rear lift, we have around 9 and change, so under 10%. If we're looking at trucks, we have a error magnitude for drag of around 2.5% for front lift, not as many data points, but around 3% for front lift and 14% for rear lift. Okay, so we've talked about elements, we've talked about where it came from and the aerothermal challenges that we're trying to accomplish, and we talked about the validation that have been done by the Auto Research Center and by ENGYS. Let's dive into some customer success stories. And this particular success story was, or at least this benchmark, was performed by Volvo. And they wanted to compare wind tunnel results versus various CFD codes versus elements. And multiple different configurations were actually tested between these three different vehicles. So we have sedan, we have an SUV, and then we have kind of a station wagon or a state back. And these results were published in a paper in JSAE, in the annual Congress in 2017, in a CFD benchmark for improved accuracy of aerodynamic simulations. In terms of the wind tunnel setup, this was the Volvo Corporation wind tunnel, so PVT, on-road conditions, moving ground, there's boundary layer control. The test velocity was 140 kilometers per hour at 0 degrees yaw. The CFD setup, it used an automatic hex dominant parallel meshing with the best practices for external aero. It is a transient incompressible flow using the delayed detached eddy simulation, specifically using the Spillard-Almaraz formulation for turbulence. So these are transient simulations using DDES. The velocity is 140 kilometers per hour and 0 degree yaw, as I've already mentioned. There's condensers, there's radiators, there's intercoolers. That porous media was approximated using a Darcy-Forchheimer model, and the cooling fans the physics were approximated using a rotating wall velocity. The moving ground with rotating wheels, so there's a moving ground boundary condition that's a tangential boundary condition, tangential velocity, and then the rotating wheels is a fixed wall rotating velocity on the wheel surface itself. And for now, we're ignoring thermal effects. So this is a cold flow experiment. So if you look right here, the red line is the experimental results, and these have all been normalized with respect to the baseline being this point right here. So open cooling baseline, this red line, and elements is actually this green line. So code 5. So we see that for CDA results for a V60, for the different configurations of open cooling, closed cooling, removing the front wheel deflector, etc., we see the magnitude and the direction of each one of these changes is very accurately predicted with elements. We see a trend for code 4, and the magnitude is slightly off compared to elements and also compared to the experimental data. And then we've got code 2 far off in terms of magnitude, and then we've got code 3, which in this case right here, completely off the mark. Code 3 again is having a little bit of difficulty compared to the rest. For CDA on results of the S60, we see fairly good agreement between code 4 and code 5 with experiment. Again, the green line is elements. So here, this is CDA results for the S60. And then CDA for the XC90. Again, we see elements performing very well against these different configurations compared to the experimental results. There's similar comparisons with rear lift for each vehicle. Here we've got experimental results on the red line. We've got the green line, which is elements. Here we have a little bit of over prediction on the rear lift for the S60 for elements, but the trend, the direction was fairly accurately predicted. A little bit of discrepancy here with the rim covers on this one example. But overall, it looks like Elements is performing very well for CDA and then CLA for the different vehicle types. So just in summary about the benchmark itself. So this CFD benchmark was performed by Volvo. They wanted to compare the experimental results with different CFD codes versus Elements. Multiple configurations were tested. Overall, the results agreed well compared to other codes. And in the end, they decided to use multiple codes. So they used code 4, and then they used Elements within their company. So another success story I want to talk about is from CRF at Fiat. And we're looking at the Fiat Bravo. This case was a DES, transient aerodynamics analysis using Elements, open cooling geometry, open road geometry. So this is kind of the bread and butter of Elements right here. And we wanted to verify the best practices for the accurate prediction of lift and drag. And within this study, there was a comparison to wind tunnel data and other commercial codes. This comparison of the other CFD codes is not actually shown here. In terms of meshing, we've got an automatic hex dominant parallel meshing that comes standard with Elements, and we're using the embedded best practices for external aero. There's localized volume refinement to resolve the wake and other important areas. There's near wall layers to model the boundary layer flow over the external areas of the vehicle. There's zonal meshing to capture porous regions. Here's a zonal mesh right here for the different radiator and condenser components themselves. For the CFD setup, it's transient incompressible flow using DES, Ballard-Almaras again. Same velocity, 140 kilometers per hour. The condenser, radiator, and intercoolers use the Darcy-Forchheimer porosity model. The moving ground with rotating wheels, again, similar boundary conditions to the Volvo best practice or the Volvo benchmark. And again, we're using cold flow. One of the important comparison points was looking at the underhood velocities. The potential customer in this scenario was interested in looking at the underhood flows, looking down the road at underhood thermal simulations. So we're able to actually capture a lot of this information and reflect that into a design phase if we need to know a certain amount of flow or convective cooling over different engine components. In terms of a comparison between the CFD results and the wind tunnel for Elements, for this case, it was about a 2%, under 3% difference in drag, and then around a 16.5% difference in lift. And these are normalized against the wind tunnel results themselves. So overall for drag, very good. And the actual underhood velocities compared well to what was seen experimentally. That comparison wasn't actually shown in much detail here, but it performed well from the perspective of the customer. The next success story I want to talk about is a recent collaboration between ENGYS and Thermal Analytics. We actually did a webinar earlier this year about Ti-therm coupling. So there is a necessity to evaluate thermal protection within a vehicle. So these panels underneath a vehicle that are close to engine components or maybe the exhaust system. So there's heat generation from the exhaust system that affect this thermal shielding. So this actual exhaust system was modeled with Titherm, and the radiation was modeled and solved within Titherm, so the radiation transport from that hot component to the thermal shield itself. The heat removal within this system is mostly from convection, so mostly from these underhood velocities that we saw within the CRF case. So it's extremely important to be able to have airflow in certain regions if you expect hot air to be trapped in a certain compartment that may degrade a certain component faster if it's not being cooled well enough. So within this study, there were two different modes. There's a moving mode, so there's heat generation while the vehicle is driving, and then there's this soaking component. So soaking might be stopping at a stoplight. So you've been driving a lot, and then now you've pulled up to a stoplight and you're waiting. So for the moving vehicle case, we're able to, so Titherm predicts the temperatures within the exhaust system and then the radiative transport onto the underbody, the body panel, these different components, and we're able to predict the surface temperatures with this coupling. And here's just a perspective of the fluid flow itself around the vehicle, and then this is just a slice in the Y direction showing the air moving through a radiator and through a fan at the front of the vehicle, and then around the engine and transmission and under the vehicle itself. So we see this airflow coming underneath, and then we see the wake behind the vehicle. The second phase of this, which is actually was more important, was this soak phase. So we've solved the fluid flow problem, and then now we've solved that to a steady state, and then we're applying a transient Titherm scenario where the radiative transport from this hot component is heating up this heat shield. And then because of that, there's buoyant flow within the system. There may be fans moving, and then there's buoyant flow. So here we've got a steady state solution at time 0. And then after 5 seconds, after 60 seconds, after 240, and so on, we can see this cool down from the airflow underneath the vehicle. So Titherm and elements coupled together were able to solve this type of problem. Now, this was just for an internal combustion engine. Similar cooling system integration and testing could definitely be done for electric vehicles. So there's lots of versatility in terms of coupling these tools together. So Titherm and elements are a powerful combination to model complex aerothermal interactions. And in the recent release, in the last few weeks of elements, there's a new thermal coupling boundary condition, which enables two-way coupling to third-party thermal solvers. It was designed to work with Titherm and Cotherm, and it supports steady state and transient thermal loading. And this is currently being used by other OEMs to collaborate between teams. Maybe you have a team that's designing this cooling system or designing other systems, and this can be used as this as a collaboration tool. All right, let me talk a little bit about Elements GUI. So here I have an animation of a case being set up. When you first start the GUI, you're met with a client-server connection dialog, and this client-server connection dialog allows us to connect with different types of resources. So here we've got a cluster back in the United Kingdom that we use quite a bit here in the US. This is my workstation back in the office, and then this is my local laptop, which we'll be working on today. So when you click connect, it generates a local client server. So here we're starting the server, and all of this is in real time. I'm not speeding anything up to make anything look better. And we can define a new case. So here, let's just define one that is generic truck. And let me place that on the desktop. And then for this particular case, I'll define 556 cores. And what that will do is go ahead and set everything up to potentially use on a cluster down the road. Now, whenever we start the GUI, we're met with the general CFD interface. There's different tabs. So meshing, setup, solver, and view. Mesh is where we would perform all of our meshing actions. Setup is where we set up all of our boundary conditions. Solver is where we actually execute the solver. And view is where we might do post-processing. However, within Elements, we can streamline a lot of this by using the external Aero wizard, which is located here in the ribbon interface. Immediately, we're met with the default configuration. The default configuration, these are the open roads defaults. These are kind of the default best practices, the recommended starting point for different companies to begin their journey of using Elements within the design process. So when you select a configuration file or a different configuration, then you can select different car body types. These are the default body types. We can add more, we can take away. You can have multiple hatchbacks, you can have multiple SUV car body types. One might be for a sliding mesh for the wheels, one might be for different tire tread treatments. So there's a lot of versatility in terms of configuration files, in terms of body type. All right, so here we'll select the pickup. Then we'll need to import our different geometries, our geometric components. So here we've got a pickup, and I'm importing all the STLs. We can import CAD files. I always suggest to customers to export STL files, and then we can import that directly into the GUI. Here we can scale, we can rotate, we can translate, we can do a lot of different things to each one of those surfaces. So here we're importing all of the different surfaces for the truck. All right, you'll immediately notice that there's different categories. So these different categories are the vehicle assembly types. So here we see the word body, and then we see the word wheels in front of these different assembly types. And there's a shortcut to automating a lot of this, and that is by adding PIDs to our surface names, and then it automatically categorizes these assemblies. It's very handy with this automation component of setting up an external aero simulation. Now for wheels, there's a different wheel interface to help us set up the rotational axes, to help us set up the different boundary conditions, to help us set up different components of the wheels. And if we wanted to, we could move these different assemblies around. So move them to body. So here I'm going to move caliper and rotor back to the body because maybe I don't want to treat them as rotating components. And I can recategorize that particular assembly type as body. And what that does is it changes how it's meshed, what kind of level of refinement, how many layers are on there. But then maybe at one last moment, I'd like to actually include the rotors themselves. So I can take the different rotors. So here, I can select all 4 of the rotors because now I'd like those rotors to be rotating to take into account their influence. And I can click on the different wheel components, and I notice that the axis of rotation doesn't line up with the rotor and the wheel itself. So I could then interact with the wheel entirely, and I can reset that value, and it actually senses the wheel location, the wheel axis. If I needed to, I could go through, there's a wheel widget in which I'm allowed to kind of select multiple points on this rotating arc to help it sense the axis of rotation. After we've selected the wheels, then we can go to the wind tunnel setup here. Here's the bottom of the wind tunnel itself, so we can have it automatically sense the floor height and adjust where all of the refinement boxes are happening on this pickup. I can adjust the yaw angle. Then I can go to the run settings. I can automatically sense the frontal area, or it's common practice to use the same frontal area even if we're changing different geometric components on a vehicle. For example, if we are adding an air dam or taking away an air dam, that might change the frontal area, but we'll use the same frontal area between these two different runs. So we're able to manually input that. Then we can automatically detect the wheelbase itself. If you have access to the adjoint optimization module, then we can select run adjoint, and this will determine the external sensitivities on the vehicle itself for minimizing lift, minimizing drag, or minimizing rear lift. So we're able to turn these sensitivities on and off. Next, we would apply the settings. And what that will do is it'll write all of the different geometric components, write the boundary conditions, write the physiochemical parameters, and then kick us out to the general CFD interface where it's set all of these things for us automatically. Here we don't have a tremendous amount of different surfaces, but we could have hundreds or thousands of different components, and we've automatically set distance refinements and surface refinements. And for the setup tab, we see that the boundary conditions are already set for all of these different components. Our data collection, so monitoring functions for lift, drag, and volume reports, that's already done. Our physics are already set. We are ready to go. And from here, if we wanted to, we could hit run all. And if I was connected with a client server connection to my HPC, it would literally kick off a meshing job. Then it would run a setup utility to set up all my boundary conditions. Then it would run the solver. Then it would run the reporting tool within Elements and generate a report automatically. So here, run all would execute mesh setup solver and in one go. All right, so that is the quick walkthrough. And you can imagine that if I wasn't stopping the video and actually continuing, that this would go much faster. And so you can typically set up a vehicle in under 10 minutes. I'm being very generous. So let me leave you with a few take-home messages. The first one is, use accurate simulation results in your design work. Elements is wind tunnel validated, not just by us, but by customers. So there's customers' success worldwide. And, half of all F1 teams use ENGYS's technology. This includes our mesher, our coupled solver module. So there's lots of technology which other companies and teams have already found extremely useful. You can remove HPC licensing bottlenecks completely. So there's no actual HPC license required to run anything on HPC. You can reduce human error by leveraging these Aero templates, and then gain more accuracy and usability within Elements by using advanced technology. So our parallel hex dominant meshing tools, the dynamic rim motion, tire tread modeling, and the powerful general CFD interface that comes with every version of Elements. Now, before we go, I'd like to plug a meeting that we're planning for September of 2021. This is the ENGYS user group meeting. You can take a look at ugm.engys.com for an agenda that is developing. Right now, it is scheduled to be held in Detroit, here in the US. So feel free to visit the website and sign up and get alerts and keep up to date about what is happening, whether that's going to be an in-person event or a virtual event for next year. And with that, I will take any questions.